Between the Atlantic and Pacific Oceans lies one of the world's most important trade routes. But behind this vital corridor stands an even greater achievement, the Panama Canal Expansion project, a monumental engineering effort that transformed global shipping. At the heart of the expansion stands the third set of locks, a massive hydraulic system built to handle a new generation of global shipping. But before concrete, steel, or excavation could begin, engineers first needed to understand the hidden landscape beneath the water. The journey started with a single mission: map the unknown. Long before construction begins, the Panama Canal Expansion project starts with one critical resource: data. Thousands of sonar pulses sweep across the Pacific entrance, mapping the underwater terrain of the future third set of locks.
Deployment successful. Data continuity established. Recovering the crane now.
Combined with satellite positioning, raw survey data becomes a precise blueprint for expansion. With the survey complete, engineers can finally investigate the geology hidden beneath the surface. Every future lock chamber and navigation channel depends on the strength of the underlying bedrock. Core samples reveal hidden fractures, weak zones, and geological conditions that could affect the entire project.
We are seeing a clear velocity increase at that depth.
The geophones along the line confirm the shallow bedrock interface.
Laboratory testing transforms natural rock formations into engineering data for structural design. Only after confirming foundation stability can large-scale earthworks begin. To create a new route between the Atlantic and Pacific Oceans, vast sections of terrain must be removed.
According to the tablet, we need to adjust the timing here.
Okay, I'll reroute the green line.
Make sure the connections are secure before we proceed.
Precision drilling prepares millions of cubic meters of bedrock for controlled excavation. Every blast follows a carefully engineered sequence designed to maximize efficiency and stability. As excavation advances, the future navigation corridor begins to emerge, preparing the canal for a new generation of global shipping. Long before larger vessels can enter the canal, the Panama Canal Expansion project must first reshape the underwater landscape itself. Powerful dredging fleets remove decades of accumulated sediment, expanding the navigation corridor toward the future third set of locks. An immense network of pumps, pipelines, and support vessels moves millions of cubic meters of material beyond the visible shoreline.
The bathymetry confirms the required depth in this section. Copy that.
Post-dredge verification complete for the channel.
Every dredge section is surveyed and verified, ensuring the channel meets the requirements of future Neo-Panamax vessels. As work shifts from water to land, a new challenge emerges: building foundations capable of resisting enormous hydrostatic forces. Massive dewatering systems lower groundwater levels, transforming unstable ground into a controlled construction environment. Rock bolts, grout curtains, and drainage systems work together to protect the future lock complex from groundwater intrusion. Only after the foundation is stabilized and secured can the project advance to mass concrete construction. Millions of tons of reinforced concrete will form the backbone of the future third set of locks. Industrial batching plants operate continuously, supplying marine-grade concrete for one of the largest lock projects ever built. Dense reinforcement systems, water stops, and structural interfaces are embedded to withstand future operational forces.
Watch the flow rate. Bring that boom over to the next section now. All right, moving it now.
As the concrete gains strength, the foundations of the third set of locks begin to emerge from the excavation floor. With the foundation complete, construction finally moves upward as the future lock chambers rise above the basin.
All right, bring it up slow. Watch the alignment on the far side. Clear below, keep going.
Self-climbing formwork systems advance section by section, allowing the massive chamber walls to grow with extraordinary precision.
How does the 20-foot mark look?
Holding steady at +2 millimeters.
All right, note that down. We'll move to the next section.
Embedded hydraulic corridors and structural passages prepare the lock system for enormous future water flows. The immense lock chambers are taking shape. The next challenge will introduce some of the largest rolling steel gate systems ever built. The Panama Canal Expansion project now enters one of its most demanding phases, building the massive rolling gates that will regulate traffic between two oceans. Inside specialized fabrication facilities, Thick steel plates are transformed into enormous rolling structures designed for decades of operation. Integrated buoyancy chambers allow these multi-thousand-ton gates to move precisely while reducing loads on the lock system. After corrosion protection is applied, the completed gates begin their journey toward the future third set of locks. Transporting these massive structures requires specialized vessels and heavy logistics systems operating at immense scale.
We are clear on the east side, lower by 2 meters.
Roger that, lowering now.
Watch the clearance on the left.
Okay, set it down.
Clear to roll.
Precision lifting systems position each gate inside its concrete niche with millimeter-level accuracy.
1.5 millimeters tolerance.
Heavy-duty rail systems and wheel assemblies establish the rolling path for future gate movement. Advanced sealing systems create a watertight barrier capable of resisting extreme hydraulic pressures. Alongside the lock chambers, another signature feature begins to emerge: the Panama Canal water-saving basin network.
We need 3 more ties on this section, quickly. On it, boss.
These massive reservoirs are designed to capture and reuse water during every transit through the third set of locks. Reinforced concrete structures, intake systems, and distribution networks control the movement of vast water volumes. When complete, the basin network will significantly reduce the water required for each vessel transit. Deep beneath the lock chambers, a hidden hydraulic network is taking shape. Massive valves, hydraulic actuators, and control systems regulate water movement throughout the lock infrastructure.
Okay, easy now. Bring it down 5 centimeters. Hold it there. Perfect, set the dogs.
Protected by steel liners and energy dissipation structures, these culverts are engineered for high-velocity flows. Completing this underground hydraulic network establishes the system that will fill and empty the locks before operational testing begins. For the first time, water enters the third set of locks as commissioning operations begin across the Panama Canal Expansion project, activating years of engineering work. Millions of liters of Gatun Lake water surge through the hydraulic network, flooding the lock chamber under realistic operating conditions for the very first time.
The pressure on Seal Charlie is fluctuating. Yes, and the leakage is increasing at joint 4. Look at the thermal reading here.
Under full hydrostatic load, the rolling gates undergo their first operational tests to verify alignment, seal integrity, and long-term performance. Successful hydraulic testing confirms the lock system is ready to advance toward its first full-scale vessel transit. The Panama Canal Expansion project now welcomes its first Neo-Panamax validation transit through the newly completed lock system. Arbor tug fleets guide the massive vessel through the lock chamber with extraordinary precision, maintaining strict navigational control. As the gates close, controlled water discharge lowers the vessel smoothly toward its next operating elevation. The successful transit proves the expanded canal is ready to support the next generation of global maritime shipping. Long after construction ends, robotic inspection systems continue protecting the lock infrastructure from hidden operational risks. ROV platforms inspect submerged rails, seals, and structural components concealed beneath the waterline. Corrosion protection systems are continuously monitored to preserve critical steel structures throughout the lock network. Long-term telemetry analysis helps ensure the third set of locks can reliably support global trade for decades to come. From the first survey vessels mapping the seabed to the completion of the third set of locks, the Panama Canal Expansion project transformed one of the world's most important maritime corridors. Today, massive Neo-Panamax vessels move efficiently between the Atlantic and Pacific Oceans through a system of locks, gates, basins, and hydraulic networks built on an extraordinary scale. More than an engineering achievement, this project reshaped global trade, strengthened international connectivity, and stands as a lasting symbol of what human ingenuity can accomplish when vision, science, and infrastructure come together.
NextGen Machine Works, building the impossible. Subscribe to join the future.